All right, ladies and gentlemen, welcome to chapter 5. And in this chapter, we start talking about nuclear chemistry. And now, nuclear chemistry is different than the other chemistry that we've looked at because when you're dealing with chemical equations, remember, it is the electrons that actually cause chemical equations to happen. When we start talking about nuclear chemistry, though, we're talking about reactions that are happening inside the nucleus. And so, because they're happening inside the nucleus, we end up with a whole new substance altogether. So, we may start out with one element, but end up with a totally new element at the end of the reaction. Now, your book in chapter 5 starts off by talking about the career of being a radiation technologist and what a radiation technologist does. And then in section 5.1, it talks about the fact that radioactivity is natural, that it is occurring all around us. Radiation is just when you have elements that are unstable, and so to gain stability, they give off either particles or energy, and that makes them much more stable. When those particles are doing that, they are known as radioisotopes. And so when we look at a radioisotope, you need to be familiar with how you write a radioisotope. So here on the whiteboard, I have an example of a radioisotope. And please notice that when you write a radioisotope, the number on the top is always going to represent your mass number. And remember, you find your mass number by adding your protons and your neutrons together. The number on the bottom is known as your atomic number. Now, sometimes in your problems will not display the atomic number. But remember, what the atomic number is the number of protons that you have in your particular element. And then the letter that's beside it, letter or letters, represents your element's chemical symbol. Now, if they give you the chemical symbol, then they don't necessarily need to give you the atomic number because you can find the atomic number from looking at the periodic table to determine how many protons there are in that radioisotope. Your book then moves into talking about the three or the different kinds of radiation that we deal with primarily in chemistry. Those kinds of radiation being your alpha particle, your beta particle, your gamma particle, and your positron, your gamma rays and your positrons. Now, you do need to know the symbol for each one of these. Please remember that when you're dealing with alpha, you may see either the symbol alpha, but traditionally we use more often than not the 4 over 2He. And what that tells you is that your alpha particle is actually a helium nucleus. So your alpha particle is going to have a 2 plus charge. It gets the 4 as its mass number from the two protons and the two neutrons that are ejected from the nucleus of this atom. And so, again, it has a mass number of 4. Its atomic number is 2 because there are two protons that are ejected. And the symbol He is used because it is the atomic number 2 corresponds to the element helium. Now, again, please remember it has a 2 plus charge, so no electrons are ejected. It's just those protons and neutrons that are kicked out of the nucleus. And now, again, because the atomic number of your element changes, that means every time you have a radioisotope that emits alpha particles, it is going to become a whole new element altogether. And so, in just a moment, we're going to look at some nuclear decay reactions so that you can see how you figure out what the new element is that's being formed. When we move on to the beta particle, your beta particle is a high speed electron. And we generally represent that using the Greek symbol for beta, or we use the 0 over negative 1e. Now, again, remember, a beta particle is a high speed electron that is ejected from the nucleus. So, if you think about it though, in the nucleus of an atom, there should be no electrons. There should be no electrons. So, what we actually believe happens with beta decay is that you have a neutron that breaks apart into a proton and an electron. And because that electron does not belong in the nucleus, it gets kicked out. Now, because electrons have relatively no mass at all, that's why the mass number of our beta particle is going to be zero. The -1 occurs because since I broke apart a neutron, I didn't change the mass number, but I did increase the proton number by 1. And so when you have beta decay, your proton number is going to go up by 1, but your mass number is going to remain exactly the same. When we talk about positron decay, in your positron decay, you have the symbol beta with a plus sign, or you can have a 0 over +1e. And what that tells you is that you have, again, that antimatter, that where that neutron breaks apart, and it gives off that antimatter that has to also again be ejected from the nucleus, because it's not supposed to be there. And so with your positron, your atomic number will go down by 1, but your mass number won't change, because again, it was that neutron that helped produce that positron. And then when we deal with your gamma rays are types of radiation that can accompany other types of radiation. So gamma is not really a particle. It has no mass, it has no atomic number, but the symbol that we use for gamma is the 0 over 0, which means it does not affect the mass and it does not affect the atomic number. And then we use the Greek letter gamma. And again, gamma can come along with either alpha radiation or beta radiation or positron radiation. And so you should be familiar with what the types of radiation are. And then your book then moves into the biological effects of radiation, and what radiation actually does to your body. Because again, radiation is natural. We're always being exposed to radiation. But the good thing is, most of us in our lifetime never get to the point where we have been exposed to way too much radiation, unless we do things that increase our exposure to radiation. Now, when we're talking about protecting ourselves from radiation, there are things that we can do. For example, if we're talking about alpha radiation, we actually can be protected from by using a sheet of paper or our clothing. So when you consider alpha radiation is not very penetrating. Um, Most of our skin is actually thick enough to protect us from most alpha radiation. However, you do have to be cautious of being exposed to alpha radiation in places where you don't have skin, like when your eyelids are open at your eyeballs. That's a place where alpha radiation can enter your body and is very destructive to soft tissues in your body. Beta radiation, on the other hand, you can protect yourself from using things like heavy clothing or a sheet of aluminum foil. It is a little more penetrating than alpha, but you still do need to protect yourself from it. And then with your gamma rays are very hard to protect yourself from. And so, in order to protect yourself from gamma radiation, you would need something like a thick sheet of lead or concrete to keep you from being exposed to what gamma radiation can do to your body. Okay. In section 5.2 in your textbook, that's where we start talking about nuclear reactions and radioactive decay. I said earlier that radioisotopes can either give off energy or particles. Well, we can write that down as a chemical reaction, but it's actually called a nuclear reaction. And so generally what we do is we start with our radioisotope, and then we show the new nucleus that forms and the type of radiation that is emitted. And so I've got an example or a couple of examples up here on the board where we can start talking about radioactive decay, looking at alpha radiation. And so in this first example, if we're looking at 64, and please notice on this copper, they don't show us what the atomic number of the copper is. But if we go to the periodic table, we see that the atomic number for copper is 29. So we can input that information into the equation. And so if it's alpha radiation, we know that an alpha particle is going to be the particle that is ejected. And so when we're considering what our new nucleus is, we've got to do some math. And it's very simple math. So just remember that whatever you have on the left side of your equation, it has to equal what you have on the right side of the equation. And so when we consider the mass, if I've got 64 on the left side of the equation and 4 on the right side of the equation, then we could write that as a math problem like 64 equals 4 plus x. And then when we solve for x, we find out that x is 60. So 60 is going to be the new mass of our new radioisotope. All right. We also have to do the same thing with the atomic number. And so our atomic number is 29. So I end up with the equation 29 equals 2 plus x. When I solve for x, I find out that x in that case is 27. And so my new radioisotope will have a mass of 60 and an atomic number of 27. And the symbol for atomic number 27 is CO, which is cobalt. All right. And so we also have another example here that we're going to do just like that one. On this one, we've got sodium 24. We know the atomic number for sodium is 11. And so, again, if it's an alpha particle, I know the particle that is going to be produced is my 4 over 2 He. When I do the math, 24 equals 4 plus x. X in this case is 20. And 11 equals 2 plus x. X in this case is 9. Atomic number 9 is represented by the symbol F. And so my new radioisotope would be fluorine 20. Again, when you have alpha decay, what you need to pay attention to is make sure that you notice that your mass number has to go down by 4 and your atomic number has to go down by 2. Now, that's a little different than when we're talking about a beta reaction. In a beta reaction, notice that your mass is not changed. So we know if it says beta, that whatever we start with, we're going to produce a beta particle, and the symbol we're going to use is 0 over negative 1e. And we've got to figure out what the new radioisotope is. So what we're going to do is we're going to do the math. We've got 15 equals 0 plus x. So we know that x equals 15. So 15 goes on the top. The atomic number for nitrogen is 7. So the equation for the bottom would be 7 equals negative 1 plus x. And so when we solve for x, we know we've got to add 1 to both sides, which means x equals 8. All right. And so atomic number 8 is representative of the element oxygen. All right. So when you look at your beta reaction, notice your mass number does not change, but your atomic number goes up by 1. Same thing when we have gold 198. The atomic number for gold is 79. And so when we do the math, we know it's a beta particle. So we're going to do the 0 over negative 1e plus Notice that our mass does not change because that's a zero. So we know we're going to end up with 198 on the top. And we know that our atomic number has to go up by one. So 79 plus one gives me 80. And atomic number 80 on the periodic table is the element mercury. All right. Now, when we go to our gamma radiation can accompany both alpha or beta. It will tell you in the problem what it does. But if there is gamma radiation involved, let's say it says alpha and gamma decay, so all you would do is add a plus sign, add your symbol for gamma, and that's all that you would do. Because I remember gamma is only energy, it's not a particle. Or if gamma was associated with this beta reaction, this beta decay, then I would just add a beta particle or a gamma ray to the end of that problem, and that would be my beta and gamma decay. Okay? Now, your book has several examples of going through different kinds of reactions. I've done alpha and beta for you. When you look at your positron, which is the other one, please just remember that with your positron, your atomic number does not go up by one, it actually goes down by one if you lose or have a positron emission. Now, in section 5.3, that's where we start talking about radiation measurements. And so in radiation measurements, we're talking about how do you measure how much radiation you're being exposed to. And it talks about the different units like the Curie and the becquerel. And how radiation is measured in people using rads and rims. And so, if you plan to work in a medical facility or any facility where you are dealing with radiation, you will have to do things like wear badges, which measure how much radiation you're being exposed to, so that you don't top out the scale for the amount of radiation that you're receiving. Because again, exposure to radiation can cause illness. And so, one of the things that's talked about in section 5.3 is radiation sickness and what the symptoms of radiation sickness are. And so you do need to be very cautious of the amount of radiation that you're being exposed to every year. And so, like, if you break bones frequently, then you need to be careful about the number of x rays you get. There is a certain number, there's a maximum number you should get in your lifetime because it can be dangerous for you. And so, please make sure you're paying attention to things like that. When we move on in chapter 5 into section 5.4, where we start talking about half life, please remember when we say half life, we mean if we start with this amount, how long will it take for half of that sample to decay and become something else? So if I started with 10 grams of iodine 131, how long would it take for that 10 grams to become 5 grams? And what we know is that for different radioisotopes, they each have a different half life. For that iodine 131 that I just gave in the example, the half life is 8 days. So after 8 days, that 10 grams of iodine 131 would actually change to only be 5 grams of iodine 131. And then you would also have five grams of xenon 131. All right, so we're talking about how long does it take for half of the sample to decay. So after one half life, that would be 8 days. After another 8 days, we would split the 5 in half, so you would have 2.5 grams left. After another 8 days, you would split that 2.5 grams in half again, so that you end up with the 1.25 grams. And so you've got several examples of half life problems, but again, please remember The half-life of different radioisotopes is different. So you do have to know what radioisotope you're talking about in order to know what its half-life is. One of the majorly important ones that we use for half-life determinations is carbon 14. When we're dating how old uh, uh, archaeological objects are, because carbon 14 has a half life of 5,730 years. It gives us a really good idea about how old ancient objects are. And your book does talk about that very briefly. In section 5.5, we move into medical applications using radioactivity, particularly the different scans you can do, like PET scans or positron emission tomography, or non radioactive imaging, like computed tomography or um, MRIs, magnetic resonance imaging, um, other types of scans that they can do where they don't necessarily use radioactive particles, but it does give you very good information about what's happening inside your body. And then in the very last section of this chapter, we start talking about nuclear fission and fusion. Please remember, when you think about nuclear fission, think about a large atom breaking apart into smaller atoms. And when you talk about nuclear fusion, we're talking about taking very small atoms and putting them together to make a larger atom. And so your book does go into nuclear reactions with doing chain reactions and also moving into nuclear power plants and talking about how they produce energies for communities. Um, Please remember that nuclear reactions do produce enormous amounts of energy because, again, when you affect the nucleus of the atom, it does take a lot of energy to change that nucleus. And so uh, when you either break a large atom apart, breaking that atom apart produces lots of energy, or if you take small elements and put them together, for example, like what's happening in the sun, the star that we use to guide our day. You see that we can see that light from that fusion reaction that's happening in the sun even as far away as Earth. So again, there are enormous amounts of energy that are being produced. However, there are risks associated with that production of energy using nuclear reactions. You can consider what has happened in Chernobyl, on 3 Mile Island, in any other nuclear disaster, as an example of some of the risks that are associated with using nuclear power. So I hope you enjoyed this chapter. It is a little different from what we will deal with in chemistry, but it does help you with writing your chemical equations, being able to express your nuclear decay reactions. But if you've got any questions on anything, please let me know. I do look forward to seeing you in our next Collaborate meeting. If you have any questions as you're working on your homework, let me know. I'm here to assist you in whatever way you need. Thank you so much. Have a great rest of your